All right, dear students, I'm here trying to give you an exercise, maybe a little bit recap of the Schmidt law that we were teaching during the lecture this week. Yeah, I think the Schmidt law has already given everybody a impression. The Schmidt law is nothing but correlating the stress on slip systems from amber crystal structures with the stress that you are applying when you have a sample, a cylinder sample or a rectangular sample, just looking like this. So we're assuming this is a single crystal, single grain structure, meaning they're not multiple crystals. So you only have one arrangement of your atoms, And basically, Schmidt law gives the geometrical and also the stress correlation between this. So that means if you apply a stress sigma to your single crystal specimen, it will only work on a specific slip system with a projection to tau. So this tau has a relationship with this sigma by this factor, which is the Schmidt factor. So cosine lambda, which is the direction between the slip direction with the force direction, and cosine phi, which is the normal direction of the slip plane with the force direction. So I think everybody followed the derivation process and you got the impression what is happening. This is really driven, this phenomenon is driven by the mechanism of plastic deformation, which is the motion of dislocations. I hope everybody got that. There was a question after the lecture asking, so we have a force projection to trigger the kind of plastic deformation, but we always know there's also another projection. If you just kind of decomposite such a force, so first into the slip direction, and you can naturally get another force, kind of opposite, perpendicular to the slip direction. That force is doing something else. If you just think about it, so you can be sure that force is not triggering your plastic deformation. Because plastic deformation can only happen to this kind of plane. But what is that force doing? That force is not doing nothing. If you think about it, I will pause just a few seconds. That force is meant to make some elastic deformation. This is the interesting part about force. So how force is really working on atoms. This is how they're working on atoms. All right. So I think that's all about the Schmidt law. It's really a very important law that you could correlate, let's say, atom level forces to a global force, or atom level stresses to a global stresses. All right. So now we spoke a little bit further about Schmidt law, because the law is simple. When we just assume there's one slip system, so one set of slip direction and plane, as we just recalled during the lecture. For FCC, we have very solid 12 slip systems, with the slip plane of 111 and with the slip direction of 110. So everybody remembers that. And for BCC structure, we have multiple slip systems, about 48, but the primary slip systems are also 12, right? With the slip plane, which is closed packing plane for BCC, that is 110 plane, and the direction is 111 direction, right? So everybody remembers all this. So that means, just imagine if you just apply a force to a single crystal again, you can easily imagine how a single crystal looks like. It's just, one particular arrangement of atoms. So when you apply that, you basically trigger, at least you have the potential to trigger slip along these 12 different slip systems. So all the slip systems, or let's say all the slip planes, they're not parallel to each other. They could be like that way, this way, this way. And that is the question. So how the dislocations will move. Yeah, if you just remember when we see from those experimental pictures, you know, the slips are always happening on one direction or one plane with, you know, repeating. So that means all the atoms, they're just choosing to go with one slip direction and slip plane. They're not just crossing each other. Yeah, that is a specific feature about this. So here I'm trying to explain you why that is happening. Yeah, so you can easily understand this stress tau. Yeah, that will be a material intrinsic feature. Yeah, because you need to reach this tau. So here we're expressing that with R, yeah, which is the critical resolved shear stress. Yeah, this stress is depending, you know, on somewhat the mobility of dislocation, but deep down it's related to the atomic bonding again. Yeah, because you need to move this dislocation. Basically, you need to break, you know, bound with existing and replace it by the motion of dislocation. So this stress is a material intrinsic number, and here I'm giving you a range. What is not exactly material intrinsic is this kind of slip systems. So which slip systems will be triggered? Now we have multiple slip systems, and which one is triggered depending on basically the following equation. So if you imagine this tau R, so the critical resolved shear stress is a constant number, and you are applying a constant stress to your single crystal. So that means the slip systems with the maximum Schmidt factor, so this guy, will impose the maximum tau on your slips, on your dislocations, right? And the maximum of this tau, if it is reaching the critical resolved shear stress, you will basically trigger dislocation motion, right? So all the other slip systems that have smaller, you know, Schmidt factor, they will be for sure, you know, less than this tau that is produced by the maximum Schmidt factor from a specific or perpendicular slip system. Yeah, so I think everybody gets this. So that means the maximum Schmidt factor will be favorable on that slip system, and then the yield strength basically, and then further derived to this. So if you know this material intrinsic number, which is tau, you know, critical resolved shear stress, and then you look for the maximum Schmidt factor you would have from a specific slip system, and then you could understand, or you could derive the required tensile stress to have plastic deformation according to such equation. Yeah, so this equation and the equation above basically will be the two forms of Schmidt law, and you can use them in different directions to either calculate the, you know, the shear stress on a specific slip system, or you can calculate also the required yield strength on your global tensile direction. And the following, I'm giving you one example to explain this. This example is very typical for you to master the Schmidt law. So basically it says a single crystal, you know, on a specific metal has a critical resolved shear stress of 20 some megapascal. So as I said, this is material intrinsic. It is decided by the motion of dislocation and decided by the atomic bonding. And this kind of crystal, single crystal, is subjected to a tensile stress of 45 megapascal. So you're trying to pull it with a certain force, generating a tensile stress of 45 megapascal. So the first question is, will yielding occur when you have, you know, the phi direction of 60 degree and the lambda of 35 degree? Basically, here I'm giving you a slip system, a specific slip system. So you don't need to calculate on your own. Actually, you could calculate on your own. If I say this is FCC and it has a certain crystal orientation, you can use knowledge you learned before to first get those two angles, and then you do the calculation. But we make it simpler. Yeah, so we just gave you those two directions are, you know, in a direction with your axial loading. So phi is 60 degree and lambda is 35. And the first question is asking, will we have yielding? So the yielding criterion on the crystal level is basically if the superimposed shear stress on the slip system is reaching the critical resolved shear stress or not. If it reaches, the dislocations will move. If it doesn't, so dislocations basically don't move. Yeah. And the second point is if this one, so 45 megapascal is not triggering plastic deformation, so how much I should at least to apply to this sample to trigger the plastic deformation. So here I show you the solutions. Yeah. For the question A, basically we need to calculate the shear stress, right? So this is the R stats for resolved shear stress. So this is not the material intrinsic, so not the tau CRSS. This is just the stress, the shear stress that a certain axial stress will generate on your slip system. Yeah. So it's very simple. We just apply the Schmidt law as its usual way. So you can just, you know, take all these numbers and do a simple calculation. What you get is 18.4 megapascal. Right? You compare with the critical resolved shear stress, tau CRSS. So it's smaller, meaning we are not having yielding. So it's elastic deformation, no plastic deformation. Right? Now let's do the second question. The second question is basically asking you how much tensile stress I should apply, you know, globally to trigger plastic deformation. And this is the second use of the Schmidt law, basically, because we know tau CRSS is 20 point something megapascal, and we just apply the Schmidt law in the second form, and you can easily calculate the required tensile stress to trigger plastic deformation is 50.5 megapascal. Yeah, I guess everybody now could easily manipulate those equations and to help you understand Schmidt law further, and most importantly, to understand the correlation between a global tensile test and what is exactly happening to your atoms in your microstructure. All right, so that is all from my side.